What if I told you time is not absolute? That the ticking of your watch depends not only on where you are, but how fast you're moving, or how close you stand to a massive object. This isn't science fiction. It's one of the strangest, most fascinating realities of the universe, time dilation. In this video, we'll journey from Einstein's theory of relativity to astronauts in orbit, from particle accelerators to black holes, and finally, to the very edges of what time means. Buckle up. Things are about to get very weird. For most of human history, time was thought to be universal. The sun rose, the sun set, and every second ticked forward equally for everyone. Newton's universe assumed time was an invisible stage, unchanging, absolute, the same for all observers. But in the late 19th century, cracks appeared. Scientists discovered that the speed of light is constant, always the same, no matter how fast you move. This strange fact shattered Newton's model. Because if light doesn't bend to your motion, then something else must change. Einstein realized it's time itself. In 1905, Albert Einstein published his special theory of relativity, proposing two radical principles. The laws of physics are the same in all inertial frames of reference. The speed of light in a vacuum is constant, about 209,792 kilometers per second for all observers. These two simple statements have astonishing consequences. If light speed is fixed, then space and time must stretch and squeeze to keep physics consistent. That means if you move very fast, close to the speed of light, your time ticks differently compared to someone at rest. This is time dilation. Moving clocks run slower. The classic thought experiment is the twin paradox. One twin stays on Earth. The other flies off in a spaceship near the speed of light, then returns. When they reunite, the spacefaring twin is younger than the one who stayed behind. Time literally passed differently for them. This isn't just theory, it's been tested. Precise atomic clocks flown on airplanes and satellites have shown measurable time differences compared to clocks on Earth. Hafele-Keating experiment, 1971. 4 cesium atomic clocks were flown around the world on commercial jets. Upon returning, the airborne clocks disagreed with those on the ground, exactly as relativity predicted. GPS satellites. GPS works only because we account for time dilation. Satellites orbiting Earth move fast enough, and are high enough in Earth's weaker gravity, that their clocks tick about 38 microseconds faster per day than ground clocks. If we didn't correct for this, GPS would be off by kilometers within a single day. Muon decay. Moons, short-lived subatomic particles created in Earth's atmosphere, should decay too quickly to be detected on the surface. But because they move at near-light speeds, their internal clocks tick slower, allowing many to survive long enough to reach detectors. Every test confirms time dilation is real. Special relativity covers speed. But in 1915, Einstein unveiled his general theory of relativity, showing that gravity also dilates time. Massive objects warp space-time, slowing the passage of time near them. This means a clock on the surface of Earth ticks slower than one in orbit. Near a black hole, time slows dramatically, even approaching a full stop at the event horizon. To someone far away, you'd appear frozen in time, while for you, everything would feel normal. This is gravitational time dilation, and it's just as real as the speed-based version. You might think this only matters to physicists or astronauts. But time dilation is part of your life, GPS navigation. As mentioned, it relies on correcting both special and general relativity. Without it, your Google Maps wouldn't work. Air travel. Even jet passengers experience tiny time shifts, nanoseconds of difference, compared to people on the ground. Particle physics. Every accelerator experiment, from CERN's Large Hadron Collider to Fermilab, must account for relativistic effects. Time dilation isn't exotic. It's woven into the fabric of modern technology. Let's push time dilation to the extreme. Near-light travel. At 99.9% the speed of light, time for you runs 22 times slower than on Earth. A 5-year trip for you equals 110 years back home. Black holes. Near the event horizon of a supermassive black hole, seconds for you could be centuries for someone far away. This was beautifully dramatized in Interstellar, when astronauts on a planet near a black hole experienced 1 hour until 7 years for observers outside. Cosmic journeys. In principle, Relativistic travel could make interstellar voyages possible within a human lifetime, but the universe outside would age thousands of years. Time dilation forces us to rethink time itself. Time isn't universal. It's relative to each observer. There is no single now shared across the universe. Events that are simultaneous for you may not be simultaneous for someone moving at high speed. In a sense, past, present, and future coexist within space-time. Time dilation is just one glimpse into this strange structure. This raises profound questions. Are we truly moving through time, or is time already there, like space, with us tracing our path across it? Time dilation inspires countless works of fiction. In Planet of the Apes, 1968, astronauts return to find Earth centuries older. In Interstellar, black hole time dilation reshapes human destiny. Countless sci-fi stories use relativistic travel as a way to bridge the stars. But unlike faster-than-light travel or wormholes, time dilation is real science. The universe already gives us this bizarre phenomenon. Think about this. Right now, someone flying on the International Space Station is aging a little slower than you. Every astronaut comes back to Earth, fractionally younger than their twin would be if they had stayed. Time dilation reminds us time is not fixed. It's not the same for everyone. And it's not just a human invention. It's a physical dimension of the universe, elastic and dynamic. The crazy science of time dilation reveals a simple truth. The universe is far stranger than our everyday experience suggests. We live not in a fixed stage, but in a dynamic fabric of space and time. Our lives, our futures, even our sense of reality, all are tied to relativity. Time isn't absolute, and that changes everything. If this journey through time blew your mind, hit that like button, share this video, and subscribe for more deep dives into the universe's greatest mysteries. And tell us in the comments, if you could travel near light speed and experience time dilation, would you do it? Even if the world you knew aged centuries while you only aged years?